Hey College Algebra. In today's video, we're going to be talking about Unit 2 of our book. And Unit 2 talks about functions, and functions is something you guys have seen in Algebra 2. But in College Algebra, we're going to recap everything you guys know about functions and extend it. We're going to be talking about range and domain and some more complex functions. Also, another thing to note is that if you're ever frustrated in class, you can just say function. It's a good way to release some stress. All right, let's get started. So up here, we have our mathematical definition of function. But what you guys really need to get out of it is that each value in A, just like our x, is paired with only one, an emphasis on only one value in B. And B is a lot like our y. And so A is our input, and B is our output. And so when we input 1 into our function, so let's put 1 into our function, we'll end up getting 2 out of it. So 1 is our input, 2 is our output, and we can also look at this as x and y. All right, so now if we put 2 into our function, we'll end up getting 4. And if we put 3 into our function, we'll get 9. And so that's how inputs and outputs work with functions. So let's determine if a graph is a function. And here, we want to remember that each x will give you only one y. So for this first one, let's look at x is equal to 1. And we can see that it only gives us one output or one y. And you could do this for every x, and notice that it will only give us one output. So this one is a function. Now what if we take that same graph and flip it? And we'll call this x and this y. Well, if we look at x is equal to 1 again, we can see that's going to hit 2 points. And a function will give you only one value, so this one is not a function. And this is a great lead on to the vertical line test. And the vertical line test is a great way to determine if a graph is a function or not. And so for this first one, our vertical line is hitting 2 points. And since it's hitting 2 points, according to our definition of vertical line test, it is not a function. All right, what about this one? Here we can clearly see that our lines are only hitting 1 point. And we keep drawing lines. They're only going to hit 1 point. So, due to the vertical line test, we could call this one a function. But what if we look at expressions algebraically? How can we determine if those are functions or not? So for this first one, we should instantly think circle. And from that last slide, we saw that here, let's go to that last slide. We saw that this did not pass the vertical line test. So here, when we go back to our algebraic expression, we can say this one is not a function. What about something like this rational expression? How do we determine if that's a function or not? Well, one thing I would do is I'd take out a calculator and graph what it looks like. Once you take it out your calculator, go ahead and put it into y equals. So we got to make sure we put our top part in our parentheses, our numerator in parentheses. We'll have 3x minus 1. Don't forget to close the parentheses, and then divide it, and then make new parentheses for your denominator, x plus 2. Okay, so let's go ahead and graph. And it seems like it's a function, right? If we were to do the vertical line test for all points, it looks like x is going to have one output. But if we look at -2 right here, it doesn't look like it's going to have an output, which is okay because right here we have x plus 2 in our denominator. And so if we had x is equal to -2, then we're dividing by 0. So something fishy is going on right there, and we'll be talking about that here in a second. Here, we have the absolute value of y is equal to 2x. Now, if we use the vertical line test on this one, we can clearly see that this one is also a function. All right, now let's go ahead and move on to domain and discuss where a function can be a function. All right, so domain, what can you legally plug into a function? So here we're looking at a quadratic, and we know that quadratics are some sort of parabola. You know, this one probably isn't drawn to scale or anything like that, but it's going to be a parabola just like this one. And if we were to do a vertical line test on any parabola like this, we can see that the vertical line test is going to pass through this graph, and so that this one will be a function. But what if we look at something a little different? Something other than a quadratic. Well, if you remember from previous units that we'd have to state our domain for each equation. Here, the first thing I would do is factor the bottom. And so we could pull a 3x from it and get 2 minus 7x. Now let's say what our domain can't be. And so our domain can't equal 0. And what about here, 2 minus 7x? So you want to figure out when 2 minus 7x is equal to 0. And so x cannot equal 2 over 7, negative 2 over 7. So we'll write it like that. And so that's what x can't equal. However, for the rest of x, for x less than 0 and x not equal to negative 2 over 7, our function right here will actually be a function as long as it doesn't equal as long as x doesn't equal 0 and x does not equal negative 2 over 7. And so if we go back to this one over here, this is a function as long as x does not equal 0, or I'm sorry, negative 2. Okay. But what if we're looking at square roots? Well, we know if we have a square root of something, that this inside, this dot, 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 has to be less than, or I'm sorry, greater than or equal to 0. So here, we're going to want to set negative 10x minus 28 to be greater than or equal to 0. Now we solve for x, 28. All right, I just have to divide that by negative 10. Don't forget that our signs are going to flip. So we'll get x has to be less than or equal to negative 28 over 10. Yeah. And if we were to reduce this, we'll get that x is less than or equal to negative 14 over 5. All right, now that we've talked about domain, let's talk about range. And range is what you get out of the function. So here, if A was our input, our B is going to be our output, or what you get out of the function. So B is going to be our range. Another way to look at it is just like the y values that you get out of your function. Now let's look at this example. What I want you guys to do is pause the video and come up with the domain and range of this function. I prefer if you guys wrote it into interval notation, but I want you guys to really struggle with this one and see if you can find the range or domain. All right, so what is the domain and range of this function? First, let's start off with domain. So our domain here for this guy, we got it from being 1, 2, 3, 4, 5, 6. So it's going to be from negative 6 2, 1, 2, 3, 4 to 4. But we also can't leave out this part of the function right here, from here to here. And so that will also be from -5, or oops, just +5, 5 to 6, 7, 8, to 8. Now notice that I have parentheses right here. And that's because this guy right here is an open dot. So whenever you see that open dot, remember it's open parentheses. When you see a closed dot like this, it's a bracket. All right, so that's our range, or I'm sorry, that's our domain. Now let's talk about our range. And so our range is going to be anything from here to here. And that's it. And so our range is going to be our closed interval from 1, 2, 3, 4, -4 to +1, 2, 3, 4. It's +4. And that should also be a bracket. Now what if we have to find values of our function? So here we'll have x is equal to -2. And so we plug in -2 into our x squared and into our x. So we'll have -2 squared plus 4 all divided by -2. And so -2 squared is just 2. So we'll have 6 up top divided by -2. And this is just equal to -3. Now, but what about x plus 3? Well, this is a little different because in the last one I said x is equal to -2. But here, think about it more as if we're putting x plus 3 as our input, and then we're going to get some output from our function. So we're going to put x plus 3 in for x. So we'll have x plus 3 squared plus 4 all divided by x plus 3. Now what you need to do is double distribute the x plus 3's up top. So we'll have x squared plus 6x plus 9. Well, since it's just a plus 9 plus 4, I'll end up writing that as plus 13 all over x plus 3. And so since we can't factor our numerator, this is going to be equal to f of x plus 3. But what about this f of x plus h? So here, we're going to look at h, it's just some number. This is going to be some constant, and we're going to throw x plus h into our x's. So f of x plus h is equal to x plus h squared plus 4, all divided by x plus h. Now we double distribute that x plus h squared. We'll get x squared plus 2hx plus h squared plus 4. We're going to divide that all by x plus h. And we can't really cancel out anything from the denominator and the numerator, so this is just going to be our final answer right here. All right, but why would we ever use that f of x plus h? Well, here we'll use it in the difference quotient. And the difference quotient is something you guys are going to see in calculus. And it's going to be extremely crucial to understanding limits and other stuff, but I don't want to get into too much detail about it because that's calculus and not college algebra. All right, but anyways, what do we do? What are we doing with this difference quotient? And so this question right here, simplify the difference quotient given the function f of x equals x squared minus 2. All we're going to do is show us f of x here and here. And so let's write out what f of x plus h is equal to. And that's just going to be equal to x plus, h squared minus 2. And then our f of x right here is just going to be equal to x squared minus 2. So let's go ahead and substitute everything in. Actually, before we do that, let's go ahead and simplify this. And so we'll get x squared plus 2hx plus h squared minus 2. All right, now let's go ahead and substitute everything in. All right, so we'll have x squared plus 2hx plus h squared minus 2. And now we're going to substitute this f of x in right here. So I'll have minus x squared minus 2 all over h. Now don't forget that negative sign is going to distribute to here and to here. And so when we do that, I end up getting x squared plus 2hx minus 2 minus over h. All right, now that we've gotten to this point, we can get rid of this x squared and this x squared, by them cancel each other out, and those 2's. And now we're left with is 2hx plus h squared all over h. Well, we can factor an h out of this one, out of the numerator. So we'll get h times 2x plus h all over h. And then we can just cancel those out. So when we simplify our quotient difference, we're going to get our solution to be 2x plus h. That'll be our final answer. So, things to remember about this quotient difference. Solve for f of x plus h, and then substitute everything into our quotient or difference quotient. So, substitute everything in. And then what we're going to do is simplify. You're going to cross a lot of x's and h's out, and you'll get your final solution. All right. So for class tomorrow, I want you guys to bring in your solutions to both of these problems. We'll go over them as a class. Anyways, I hope this video is beneficial. Make sure to ask questions tomorrow if needed.